Hello and welcome to the third unit of the module on control, and this unit is concerned with control signals for complete instruction execution. So, if you look at the flow in the last basically 2 units, we mainly covered about what is a single bus organization, how different components are connected, and then we have looked into that for a given instruction what are the very broad kind of control signals required and what are the timing diagrams required involved in generating the control signals to execute this instruction. In this unit, as we have seen, we will actually look into depth of the control signals, how they are generated in a single bus architecture, and we will look in details that how these control signals are required or executed to implement a complete instruction. That is, we will take some instructions and we will see how different control signals are generated or are required for the complete instruction execution. That is what is the content of today's unit. Basically, what we will be covering in this unit, the unit summary will basically have a quick revisit. As you can see in the first point, we will be quickly revisiting what is a single bus architecture, because that is what is mainly we are dealing with all the examples, and most of our study is basically on a single bus architecture. Then we will look at where the ALU is connected, what are the different type of registers, what is the program counter, instruction register, their interconnects, all these things will have a quick recollect. Basically, and then because as we know there are multiple bus structures also like 2 and 3, but that is slightly more advanced and we are not going to look at in much details in this course. Then we quickly jump to the different cycles of an instruction like fetch, decode, execute, and then we will exactly see that what are the basic control signals required in each of these cycles. And then we will see that for any cycle, any instruction like fetch, decode and execute, we will see that for some cases which part of the control instructions or control signals are similar and for which part basically is differ. Like for fetching an instruction, it will be same for all the instructions, because you have to fetch it from the memory. So, more or less the control signal sequence will be similar for any instruction in the fetch phase. Decode phase is nothing but basically you take the instruction from your memory data register to the instruction register and try to find out what happens. So, initial part may be similar and the next part will be different if, for example, if it is a direct instruction or if it is an immediate instruction, if it is an indirect instruction. For more complicated instructions, we have already seen in the last unit that you require more cycles of execution in terms of control units, etc. Or in fact, in the last class or last units we were looking at these control instructions or control signals in terms of micro instructions. So, more the number of micro instructions or different are the types of micro instructions for a given instruction cycle, different will be the control signals. So, that we will see how we differ mainly for decode and execute cycle. Basically, in a nutshell what we will see, any first step of the instruction, basic instruction flow, that is basically your fetch. So, fetch basically what happens, you take instruction from the memory and basically bring it to the instruction register. That is the first part of the instruction. So, we will see what basically in the unit, we will first see what are the basic type of control signals required to do that. Basically what happens, first you see it will output the, it shows that output the contents of the PC to the bus. Because the program counter only will point out that which instruction has to be executed. Then the contents of the bus will be loaded into the memory address register, because then the program counter value will be loaded to the memory address register and the memory is in read mode. So, what will happen? Basically based on the contents of the program counter, basically you will load the value of your instruction, that is because from the memory address register it will tell you where the instruction is obtained and it will be loaded to the address, it will be loaded to the memory buffer register or the memory data register. And in fact, also in this instruction you will also have to increment the program counter to the point to the next instruction. So, what we do, we also instruct the ALU to perform addition. In this case it will add the value of program counter which is now in the bus with the increment. So, if the instructions are 1 bit, memory width, in one memory word, then you will add 1, and in other case if it is a 2 word instruction you will add 2 and so forth. So, basically the first step of the instruction basically loads the instruction from the memory to the instruction register, it initiates and it will also increment the value of program counter to point to the next location. Then you select the marks control, that is one operand of the ALU to the constant, that is you are going to add program counter whose value is in the bus to a constant. So, we have already seen in the last class that basically in the ALU one of the operands can be a constant or a register value. In this case we keep it as a constant. The constant value here is nothing, but it is the length of that instruction. That means, you are by adding it to the present value of the program counter, you will point to the next instruction. Then you will load the value of ALU to a temporary register. So, the temporary register now has the value of PC equal to PC plus this constant. So, what happens in the first stage, basically what we have done, if you can look at the last comment, what it says, in the first step load the value of program counter to the memory address register, increment the value of PC and store it in a temporary register. Also the memory is set to read mode. That means, now your memory is pointing towards the at the memory location where the current instruction is there, so that it can be read into the memory buffer register in the next step, and program counter has been incremented, but the increment value of program counter is now in a temporary register, not yet uploaded to the program counter. Next what you do? Next output the content of the temporary register to the bus and input the content of the bus to the PC, because at present the temporary register is holding the value of PC plus constant. You have to dump it to the bus and the bus value will be dumped to the PC. So, now the program counter will have the value of PC equal to PC plus 1. Now, you have to wait till the memory signal is ready. Basically what happens, whenever we are giving a read command and you have given the data, that is the PC value to the memory address register, you have to wait for some amount of time till the memory says that I am ready and the instruction is now loaded into the memory buffer register. So, basically in the second step, this control signal loads the updated value of PC from the temporary register to the PC and halts the CPU till the memory read signal is active. That is what it has done, output the contents of the temporary register to the bus, because temporary register, as you have seen in the previous instruction, has the value of PC plus constant, then input the value of bus to PC. So, now PC is incremented, because we do no longer require the PC value as of now, because the PC has been loaded to the memory address register. In the third stage what happens, outputs the memory data register to the bus, because in second step you already know that the memory is now ready. After the memory says that it is ready, that means it has dumped the content of the memory value which was pointed by the memory address register to the memory data register, and whenever it says that I am ready, the second stage starts. In second stage what you will the third stage starts whenever the memory says that I am ready. So, the memory data register value will be dumped to the bus. So, what was in the memory data register? It was the point of the memory that was being pointed by the program counter. Basically, it was containing the instruction. So, the bus value will now go to the instruction register. So, in this third stage what happened? The instruction is now loaded into the instruction register from the memory data register. So, in the third step, the control signal loads the value of memory data register to the instruction register after the memory read signal is active. That means, the memory has said that whatever was required by me, what was asked from me to be dumped to the memory data register is now ready, you can read it. So, after the third stage, the instruction has the IR has the instruction that needs to be executed. One important point to be noted, that step 1 and step 2 and step 3 are actually implying the memory fetch, that is instruction fetch. Instruction fetch means you load using the value of the PC, point to the location in the memory where the instruction is stored, increment the value of PC and then increment the value of PC via the arithmetic logic unit by adding a constant. The PC is incremented, at the same time you have to wait till the memory says I am ready. Once it is ready, take the value of the memory data register, data register or the memory buffer register and dump it into the IR register, instruction register via the bus. This will be same, that the 3 stages or the 3 micro instruction and the control signals will be same for any instruction, because they correspond to fetching an instruction. After that, step 4, 5, 6 actually depends on what are the type of instruction it is, what is the addressing mode and what it pretends to, and what is this to be done. For example, the value of M, i.e. the memory location from which the data is to be read is loaded into the memory address register from the instruction register. What is this saying? It is saying that now your instruction register IR is having the value of your opcode, and also you have some say R1, some instruction example I am taking, and some M. So, basically what it is saying, or in fact let us make it simpler, instead of R1 let us call it accumulator. So, it is saying that you have to take the one operand from the memory location which is M. So, in this case what will happen? This address will be loaded to the memory address register, so that in the next cycle you can fetch the value from the memory location which is given in this point. So, you can see step 4 says that the memory location, memory is made read because you have to read the operand, and the value of M is loaded into the memory address register from the IR. That means the IR is now being decoded and it is going to execute. So, before execution it is decoded that it has to read the value of the operand from the memory whose location is M. So, that value is loaded to the memory address register. This part is done by step 4, but in fact you have to remember that it is very instruction specific. If it is an immediate mode of operation, then such a step will not occur. So, that means 4, 5, 6, 7, 8 like that, it will depend on different type of instruction mode or the instruction type. Again you are in a read mode. So, in step 5 you have to wait till the memory says that I am ready, because now in the first 1 to 3 stage you are reading the instruction. From step 4, 5 and 6, in these steps are involved with reading the operand from the memory. So, you are saying that wait for the memory to respond. So, again once the memory has responded, now the value of M, that is you have to load the value, that is the operand which was stored in the memory location M is now loaded into the memory data register. Now, in fact you have to remember that whatever data now we are loading in step 5 is a data and not an instruction. So, this will not go to IR, basically it will be added with if the opcode is load. So, basically it will actually load the value in accumulator or R1, in this case it is called R1, but our example was for accumulator. 6th is the present value in the memory data register is loaded into the register. That means here I have mentioned accumulator, but it can be R1, R2, anything. So, basically 6th step actually executes the instruction. It takes the value from the memory location, memory M, which is now present in the memory buffer register. So, this one is actually presented in the memory data register or the memory buffer register. Step 5 clears that memory is saturated, means memory is ready, data is available in the memory data register, and then in the 6th stage you will dump the value of the memory data register, basically which is containing this operand into the accumulator or register R1. So, in fact 1, 2, 3, again I am repeating, this is actually the summary which we will be covering in this unit for different type of instructions. So, step 1, step 2, step 3, that is instruction fetch will be similar for everything. 4, 5, 6, 7, 8, 9 will depend on the instruction type. So, basically what are the basic objectives of the unit? The first is a comprehensive objective, in which case you can explain the generation of control signals that is driven by the internal organization of the processor. That means given a single bus architecture, which is the main focus of this unit, given a single bus architecture, you will be able to basically explain how different signals are generated for each of the micro instructions in a very detailed manner, which will require for a complete instruction execution. Then next, the design objective, you can explain the design of complete control steps to execute instructions like ALU, operation, data movement, etc. And the different operations type like load, data movement, store, auto increment, decrement. For such type of different type of instructions and instruction type of instructions and the addressing mode, you will be able to design a complete steps that needs to be followed for generating the control signals for executing the instructions. Now, we are going to again revisit the detailed system bus architecture, single bus architecture in details, but again we have to see the slight details we have compared to the previous unit. So, this program counter, this is your single bus, then you have a memory address register which is connecting, in fact actually it is a slight mistake basically, in fact the memory address register is a unidirectional bus, so it should not be there, it is a unidirectional bus. So, in fact which is connecting, so it is giving the input to the memory. So, whenever depending on read and write mode, your memory bus, it will dump the value in the memory data register if it is a read, and if it is a write, the data from the memory data register will go to the memory. This is your instruction decoder, which is basically decoding the instructions and generating the control circuits. This is very important. And who is going to feed to the instruction decoder? The instruction register. The instruction register will again get the value from the bus and it will go to the instruction decoder, which will decode in terms of control signals based on the instruction to be executed. You can see there are different registers R0 to Rn, they are all the registers like general purpose registers. It will depend on 16, 32, 48 or 16, 32, 64 depending on the type of processor you are using. So, this is the general purpose user, there is a temporary register or a scratch pad, and this is very important part, you have to look at it. So, this is your arithmetic logic unit part. So, you can see this is your ALU. So, in the ALU one input is coming from the bus. So, generally it will be service, it will actually take one operand which is available in the bus. So, this part or this part of the ALU, the right hand side part of the input to the ALU basically takes the data from the bus, which generally is an operand. But the left hand side you can see it can take data from a register. Y is a special register, sometimes we call it accumulator. So, it is going to take the data from the Y as an input, or in some other case it can also take as a constant. So, it is a multiplexer, the multiplexer is a select line. So, now you have to very importantly keep this in mind, that this part. So, either the accumulator or the ALU will take data from register Y or a constant. So, when is a constant? When is basically you have to increment the value of PC. So, whenever you have to increment the value of PC, at that time the constant will be given, constant will be the length of the instruction. And of course, there are different modes of operation in the ALU like add, subtract, increment, that will again tell you based on the operation type. Is an add instruction, load instruction, and load instruction, subtract instruction, increment instruction, any type of ALU instruction that will be commanded, the signals will determine that. For example, if you have to add two numbers, it will be in add mode, subtract, multiply and so forth. But most important is this part. If the value is coming from Y, then it is generally an operand which is already loaded in Y. But if you have to increment the value of PC, at that time generally what we do, we take the value from this constant. So, constant is basically your the length of that instruction. So, that PC equal to PC plus constant, that means it points to the next instruction. In that case, select line in the multiplexer will determine that. So, again I request you that please look at this part in more careful manner, that is this part, please look at it very carefully. Okay. So, again we will keep on revisiting this, that is not a problem. Now, let us go to this in details. So, there is a program counter. So, this is your program counter. So, whatever I was telling is written in this. So, basically program counter, as we have discussed so many times, basically holds the present location which has to be executed. So, generally in the first step of control instruction or first micro instruction, the value of program counter is loaded to the memory address register and it is incremented. So, based on that instruction is fetched and the work starts. Then there is something called memory address register. As I told you, it actually tells the memory that what value, what register, what location of that memory has to be read or written. So, generally when you are fetching an instruction, the value of the program counter is loaded into the memory address register. If there is a store instruction, then when you are saying that store accumulator to memory location M. In that case, the M that will be actually present in the instruction, that value will be taken from the instruction register, the M, and it will be loaded to the memory address register. So, basically memory address register tells that which memory word has to be read or written. So, therefore, actually there are two kind of address, one the address of an instruction that is generally taken from the program counter, and address of an operand. So, address of an operand is available in the instruction. So, it is generally taken from the instruction register. Okay. So, the next is the memory data register. As you look at this slide. So, memory data register is nothing but a buffer which will take the data from the memory to the bus. Before that, if you think that this is your memory and this is your data bus, so I generally have a buffer over here, which is the memory data register or memory buffer register. So, basically immediately you cannot read and write from the memory. So, you give a read command, then you have to wait for certain amount of time till the data from the memory will come to the memory buffer register, and then it will say that I am ready, that is data has been given, then only the bus can read it from the memory buffer register or the memory data register. Similarly, if you want to write also, you put the value in memory data register and then you give a write command to the memory, but you have to wait for some time till the memory say okay, then you know that the data has been read from the memory data register to the memory. So, therefore, there is a buffer in between. Then arithmetic logic unit, nothing to tell much, it can do all arithmetic and logic operation. But one important thing, basically you can see that it is connected via Z. That means what? That is because you have to because the output of the ALU will be dumped to Z, which is a register, so that it holds for some amount of time, that is for 1 clock unit of time, so that it can be given to the respective place. So, the output of the ALU is stored in a register called Z, which holds it for some time before we take the value, and the ALU can be reused. Because if I do not store the value of register, if I do not store the value of the output of ALU in Z, then you can have some kind of a problem, like there can be overwritten, that maybe I am storing the value of 3 which I have got in the last clock part, but if I do not store over here, then actually if some new value come over here, there can be a corruption in the output. So, therefore, we have a temporary register or a register Z which holds the value of ALU outputs for some amount of time. That is what is the arithmetic logic unit. Instruction register, nothing to tell more, it takes the instruction and knows what to do. Instruction decoder, basically it is a normal decoder circuit, it will take the instruction, because all instruction has the first part as opcode. So, it will take the opcode and accordingly generate control signals corresponding to that opcode. Registers, as I told you, shown from R0 to Rn minus 1, they are all general purpose registers. It depends basically on what is your processor type and what is your processor. So, it can range from 4 registers to 32 registers and so forth. Then we have multiplexer and constant. So, this part already I have told you many times right now, but again let us focus. So, what it says is this part. So, this is your ALU and this is your register. Basically, this is your marks and this one. So, basically as I told you, the ALU can either take input from Y, then it will be an operand, or it can take a via multiplexer this constant. So, if this constant means it is for incrementing of the PC. So, that is what has been told over here, that multiplexer and constant, what are the meaning. Basically, instead of Y which is an operand, it will take the value from the constant which is for increasing the value of program counter. So, with this basic background in mind, we will now see for different instructions what are the control signals generated in full flow of instruction. Now, one thing before we go, one thing you have to remember that for example, there is something for everything, there is a command involved called in and out. So, for example, if I want to say that the value of register Z has to be dumped to the CPU bus, then you will write Z out. That means the value of Z will be dumped to the bus. For example, the value of PC, but PC has to read the value from the bus. So, in that case what you will do? You will write PC in. That means what? PC is going to take the input from the bus. As already discussed in the last unit, you cannot have simultaneously Z out and PC out. In this case, PC will be dumping over here, Z will be dumping over, there is a conflict. So, those things has to be actually avoided, correct. So, sorry. So, now what we will do, again it is a slight mistake, it is a bus. So, now what we will do, now basically we will take this instruction load R1M. So, R1 is one register, user general purpose register, M is a memory location. So, what will happen? You read the value of memory location M, whatever variable value is this in operand has to be loaded to R1. So, that is what we are going to do. So, first we will fetch this instruction, decode it and then execute it. We will see all the steps in details. So, first what is the first step? That you have to, as I already told you in the summary, the first stage actually will involve writing, because you want to basically first stage is you want to fetch this instruction. So, in which memory location load R1M is there, that is been actually known by the program counter, because program counter always points to the next instruction. So, only the program counter can tell you where basically this instruction is at present in. So, what happened? The program counter value will be loaded into the memory address register and you have to make the memory in the read mode. So, that is what is being said. So, program counter value is PC out. PC out means the value of program counter will be dumped to the memory bus. Now, where it will go? It will go to the memory address register in. That means the value of program counter will go to the memory address register. That means now you are pointing to the next instruction which has to be fetched. You are making it read, that the memory is in read mode. Now, this part actually corresponds to PC out, memory address register in and read. These three control signals basically specifies that I have to read the next instruction from the memory which is pointed by PC. Now, you can see it is making say select 0, add and Z in. So, what does it mean? It select here means, select 0 means, we will again see this corresponds to the multiplexer. Select 0 means you have to add the constant and not the value of Y. Add here means what? Add here means the ALU is in add mode. At Z in means the register Z will take the value in from the ALU. So, let us look at it, what does it mean? We will be revisiting it many times. So, what it was saying? It is saying that PC out. So, PC out means it is going to give the value over here in the bus. It was saying memory address register in, that means the value of program counter is going to the memory address register. At the same time, it was saying select is 0. So, if the select is 0 means the constant will be fed over here. So, the memory address register PC value is going to the memory address register as well as it is directly coming to the ALU by this part, because it is in the bus. PC program value PC counter is in the bus. So, this is what is the case, and we are saying that is why select is equal to 0, and at the same time we are saying that add, that means you are going to add it, and we are also saying Z in, that means what? Your PC out value is going to the memory address register. At the same time, the other input to the ALU is PC. This part you are going to say select is 0, so you are going to get a constant. If the instruction size is a 1, so you are going to get put it 1 and you are going to get as 1, and Z in, that means the output of the ALU which is nothing but PC equal to PC plus 1 is going to the Z. So, you are executing three basic things. You are incrementing the value of program counter by the ALU, loading the value in Z, and also you are loading the value of program counter to the memory address register so that the instruction can be fetched. At the same time, memory also has been made in a read mode. So, these are the signals which corresponds to the first stage. Let us again clean it up, because we will have to revisit this figure many times. So, again I am cleaning it up. So, next is what? Now actually next stage is, till now we have seen that the output of this PC equal to PC plus 1 is memory is in register Z, and memory has, you have given the command to read the memory. In second stage what we do? So, whatever I told you about the first point is written over here, you can read it. Now, what it says, Z out PC in. Now, what the Z had? If you look at the initial last slide, then Z had the value of PC equal to PC plus 1, but at that time it was Z in. Now, I am making a Z out and PC in. That means the value of Z will go to PC program counter via the bus, because Z out and PC in, and we are waiting for WFMC. So, we are waiting till the memory says that I am ready, and whatever you asked in the first stage has been dumped to the memory buffer register. In fact, again revisiting. So, in this stage what I am doing, you are making Z out. So, the value of Z is over here. So, this is Z out, and PC is now becoming PC in. So, the incremented value of PC is going to this one by this path. So, PC equal to PC plus 1, or the constant is loaded into the PC, and also I am waiting for WFMC. That means, if the signal is 1, that means what? The value of that memory location where the instruction was there is loaded into the memory data register or the memory buffer register, and now you can read the instruction to the instruction register. So, in the second stage, PC in means data will be read from this memory, this Z, which is actually nothing but PC equal to PC plus 1, and it will be read to the PC by this bus. So, the two signals Z out and PC in accomplishes that, and we are waiting till basically our memory is ready. So, that is over here. After that what happens? Now, the memory is ready. Now, what you have to do? You have to load it into the load the value of this instruction into the instruction register. Very simple. You will make memory data register out and register in. As simple as that. Just have a very quick look. So, now your instruction is over here, you have to load it to the instruction register. What will you do? Very simple, MDR out and IR in, it will serve the purpose. Basically, what is being done in the fourth instruction, fourth step. These are the two control signals which is generated in the fourth stage, this one. Then again what? Now, what is your instruction? That is 1, 2 and 3 will be same for all instructions, because that is the instruction fetch. Now, instruction has been fetched, it is in the instruction register. Now, you have to tell what I have to do. So, what was the instruction? The instruction was basically load R1M, that is whatever is present in the memory location, that is load R1M. That means, in memory location M, whatever value is there, data is there, you have to load it into R1. So, now what? So, you have to take this value M and load it into the memory address register, because that part is going to tell where the operand exists. So, obviously, first instruction will be IR out, because the value of the instruction which is present in the instruction register has to be given into the bus, and then your memory address register basically will read the value from M. Now, what there is some subtle thing over here, we are not and memory has to be in read mode of course, but there is slight thing which we have skipped over here, that is the whole instruction register will have load, then R1 and M. We need to load only this part of the instruction IR to the memory address register, because we do not require the opcode, we do not require the address for R1. In fact, the instruction decoder will take care of that. So, that part we have simply obstructed, because we just require to clip this part, which is a very simple digital operation, that only this part has to be loaded into the memory address register. So, we will do that, and then again wait till your memory read operation is complete. So, you can see the R1 has the entire instruction opcode, R1 address and address for M, that is just 3 parts basically, as I have told you, but in fact, we are going to only use this part to be loaded into the instruction memory address register. So, that clipping part we have dropped over here. Then at fifth stage, we wait till the memory says that I am done with it. So, once the memory says I am done with it, that means the data, this M data is now loaded into the memory data register. So, now what you will have to do? You have to just dump the memory data register value, that is MDR, into R in, that is R1. So, MDR out means whatever data is available in the memory data register, it will be out and it will be present in R1. So, in 6 stages I complete the instructions. Let us quickly look at the 3 controls in this figure again. So, now what happened? The instruction recorder via instruction register will load the value of M. So, this one will go to the memory data register. So, of course, it is IR out with slight abuse of notation, because I am not going to take the entire IR, only the M part of IR and MDR in, and memory is in read mode. Wait for some amount of time, that is phase 5, and then once it is done, the data has come. Sorry, just a small mistake. The M part of this one has gone to the memory address register, not the data register. That is load R1 M. So, this M part actually goes to memory address register via the instruction register. So, IR out and MAR in. You wait for some time, which is signal number stage number 5. After that, the value has come over memory data register. Now, it has go to register R1. So, as simple as that. Now, we are going to make as MDR out. Of course, all these things have now all become 0, that IR, all these things has to be go off. So, MDR out will be 1, and also R in, R1 in has to be 1. So, in fact, this one will go from here to here. So, it is done. So, all these stages are complete. So, last 3 stages basically reads the value of M from the instruction register, writes it in the memory address register, waits till the value of M is dumped to the memory data register, and then the value of MDR out will take the value from MDR and it will load to R1. So, your job is done. So, in 6 micro instructions and the corresponding control signals, what we have done? We have shown how a complete instruction is fetched, decoded and executed. So, this was about the instruction load R1M. As I told you, we will look at different instructions. So, that was just a load instruction. So, in this case we are going to see another arithmetic operation. So, in this case we are saying add R1 R2. In this case the value of R1 will be added to R2 and stored in R2. Again, as I told you, the first stage program out, PC out, memory address register in, read, select, add and Z in. This stage program counter incremented, stored in Z, move to PC and wait for WFMC. Once it is done, then MDR out and put in IR. That is, first stage points to the memory location where the data is stored, address is where the instruction is stored, plan to increment the program counter, really increment the program counter by ALU, dump it in PC and wait for some amount of time. Once it is done, take the instruction from take the instruction from MDR and put it in. So, these 3 stages basically corresponds to any instruction fetch, whether it is add R1 R2, whether it is load R1 M1, the first 3 stage basically this one and this one will remain constant for everything. Now, from here based on the addressing mode and the instruction type, things will start becoming changed. So, this one is all corresponds to fetch. So, no changes over here compared to the previous case. So, now in this case what I am having, so next instruction is add R1 and R2. So, it was add R1 and R2. So, now what is going to happen? So, how I will do it? Basically, there is one operand in R2, one operand in R1, both has to be added and the value has to be stored in R1. So, in fact, here there is no question of accessing the memory again. So, unlike the previous case, here we will not take any memory, we will not take the instruction from IR and put it into the memory address register and again read the memory, not required, because everything is in the registers. So, basically what it does, it says that R out 2 and put it in Y in. So, what is doing? Taking the value of R2 and putting it in the Y. Why? Let us quickly look at the figure again. So, what it is doing? It is taking the value of R2, some R2 which is connected over here, some register, so that it is dumping it to Y. So, this value I am putting it over here. Now, what will happen basically? So, what I will do, that R2 value I will first store it into Y. Then what I will do? Then I will take the value of R1, which is again another register over here, and I will connect it to here. So, first what I will do, the value of R2 I will store it in Y for a temporary. Then Y will have the value of R2. The next is what I am going to do. Next is I am going to just connect it to R1, so that it goes to the ALU directly, and in the mark select will be equal to 1. So, basically so select will be equal to 1. If select is equal to 1, then R1 will be directly fetched to the ALU through this part, and Y, which is nothing but in your case R2, will be coming to the ALU, and obviously in ADDO mode. So, here you will have the value of R1 plus R2. So, that is how I will do. I will store the value of R2 to Y first, then next stage I will directly connect R1 to ALU by the bus, as simple as that. Select will be 1. So, I will have the value of R2 to R1, which I have to store in a very temporary manner to register Z, and then I will again dump the value of Z to register R1. So, this will be the stage it will go through. Okay. So, this is the overall idea. Now, we will individually take the steps and clear one at a time. Now, let us again go step by step. So, next is R2 Y in. So, already we have told R2 means the value of register 2 is damped in Y in. Next what? Next already your Y, that is your, if you look at it, this is your ALU and this is your register Y, and which is coming here by a multiplexer. This is your marks, and this in fact is your pass. So, next stage what I have done, I have said R1 out. So, R1 was somewhat connected over here. So, I am making R1 out. So, the value of R1 is going in that direction. Already we have discussed, but again I am just redrawing it. So, value of R1 is going over here, which is the next operand which is connected to the ALU. Now, Y, which is having the value of R2 previously, is actually temporarily holding the value of R2. Now, this one you have marks, you have made it 1. So, it is being fed over here. So, now it is you are doing R1 plus R2, that you are going to add. Now, where I am going to store, as you already seen that you have Z in. So, Z in will actually temporarily store the value of R1 plus R2. Now, what? Next stage, this Z is also connected over here. In the 6th stage, you will make Z out, the value of Z out will come over here, and now R1 will be R in, R1 in. So, now this will no longer be in this mode, it will be going in the 6th stage, that is will be going in the reverse mode. So, it will be R in and it will be Z out. So, value of Z R1 and R2 via Z will go to R in and your job is basically done. So, in the 6th stage Z will be out and R1 will be taking the input, and so these are the 6 signals which have taken care at R1 and R2. If you compare load from a memory location and load from R1 and R2, these are register mode instruction and that involved a memory mode. So, there was a memory. So, in the 2nd stage also you have to load the memory, you have to, in first stage you fetch the instruction from the memory, in the 2nd stage actually you have to get the operand from memory location A. But in this case what happened, we have never gone to the memory for the second time because everything was available in the register, right. So, now let us quickly have a look at what are the different register values when we are executing this instruction. So, first instruction, like as I told you, the first 3 instructions, that is program out, memory address in, read, select 0, add and Z in. Then again the value of Z out is going to the program counter, wait for some time, and the memory data register will go into the register in. That means, first one corresponds to reading the data instruction from the memory as well as setting to increment the program counter. This one actually increments the program counter, and third one actually reads the value of the instruction from the memory to the instruction register. This corresponds to instruction phase. They are same for everything. Let us see step 1, 2, 3 what are the values of the registers. So, let us assume that the program counter has the value of x, x may be 1, 2, 3, 4 depending on which position of the program you are in. So, what happens? So, program counter I am assuming the value of x. So, you are dumping the value of program counter to memory address register. So, what is going to happen? So, if the value of program counter is x, the memory address will also have the memory address register also have the value of x. Memory is in read mode, select mode, nothing to do, and you are in add mode. So, what is going to happen? If you look at the architecture, this was your main bus, PC you are dumping over here, which has the value of x, and this is your ALU. So, x is going over here and you are making it add mode, correct, is in add mode, and you are saying that this select is equal to 0. Select is equal to 0 means you are going to add a constant. So, it will be constant plus x. So, in this case they have said that, and the output is also to Z in. If it is Z in, so Z1 will be written by the value of the output of the arithmetic logic unit. So, in this case we are assuming the constant to be equal to 1. So, you are going to get Z equal to x plus 1, that is PC is incremented by 1, and we are assuming that register R1 and R2 are having the value of x1 and x2, which will be 5, 6, 7, 10, 11, 14 whatever, which one you need to add. So, after the first stage you can see the value of program counter which was x is incremented and memory address register has the value x. That means, now in the next stage basically the program the memory location x will have, who has the instruction will be loaded to the instruction register. Now, next what happens? Next is you can see Z out PC in, that means the value of Z will be now out and it will actually write the program counter in a reverse manner. So, of course, the value of Z will be written to program counter PC is equal to PC plus M, and also we are waiting for WFMC, that is you have to wait till the memory is saturated, saying that the data has been peacefully read from the memory to the memory data register. So, the instruction add R1, R2 was available in the memory. So, if you look at the memory, so here the instruction was there, that is add R1, R2, and this was actually memory location M. So, now it has come over here, that is in the second stage, and finally, in the third stage basically when you are saying MDR out register in, that means memory data register value will be actually equal to the instruction register. That means, now what you have done in 3 stages, this memory location M basically, in fact it should not be M, basically it is X, I am sorry, memory location X, we are remarking with X, this memory location X, which is having the instruction add R1, R2 is being fetched from memory location X and it is dumped to the instruction register. So, instruction has been fetched. Now, we are looking to the next slide. Now, we are going to go to the add. So, this was the stage. So, next what you are doing, you are saying that R out is equal to Y in. Already we have seen that this is your ALU and this is your R2. R2 should be fetched to Y, means a temporary register over here. So, here the marks will set in such a manner, this is Y. So, that it will not take a constant, it will take the value of R2 as a operand. So, in the second stage you are saying that R2 equal to Y in. So, R2 basically had the value of X, which will be dumped to memory location Y, I am sorry, register Y. So, you can see this has been dumped over here. So, now it is actually having the value of X2, this is Y. And another, if you remember, this part of the ALU is directly connected to your bus. So, in the second stage the value of R2 is dumped into Y, which is nothing but X2 is one operand of the ALU, which is ready. Second stage what you are doing here, that is the fifth stage in this case, you are saying R1 out, select 1, add and Z in. So, you are saying R2 out. So, if you are saying R2 out means what, sorry, R1 out, that means what, this is R1 which is now feeding the bus. So, it is having the value of R1, R1 is nothing but your X1 over here. So, R1 is having the value of X1. So, X1 is going, X1 is coming to the ALU as the second operand. So, this is your X2, sorry R1, sorry this X1, sorry X1 is coming over here, correct, and then ALU already having the data in the other operand as X2. So, output will be X2 plus X1, right, there is R1 and you are making select equal to 1. So, one select is made to be 1, the multiplexer will take the value of Y, that is X2 to the ALU, constant will not be added, add is the symbol that is going to add it. So, that is the adder now, and the output, that is X1 and X2 will be dumped to Z in, because that is where it is connected to a register which is Z. So, it will come over here. So, you can see PC has been incremented. So, it is continued from here to here, memory address register is X, there was no change, Z is having the value of X1 plus X2, Y is temporarily holding the value of X2 which is continued over here, and the R1, that is register R1, that is again having the value of X1 is feeding the ALU directly from the bus without any primary, without any temporary register. Last stage what we do, we say Z out equal to R1, that is now the value of Z has to be, the value of Z has to be fed to register R1. So, what you will do, you will say Z out and R in. So, in this case the R1 which was initially having the value of 1 is updated with the value of X1 and X2, that is this value actually comes over here and your job is done basically. So, again you can have a very quick look at this figure. So, I am cleaning it off and it is very simply you can understand the illustration. Okay. So, with this we come to the end of this unit, and before we quit basically we always have some template questions and we see how the objectives has been achieved. So, the first question here is draw the diagram of a CPU with single bus. In that design you need to explain each component, write down the control steps for fetching an instruction, briefly explain the actions in terms of control signals in each step. So, basically if you are taking a single bus, if you are taking a multiple bus, basically the first 3 stages in case of a single bus corresponds to fetch and that is constant. So, if you are able to explain this as we have already done in the first few slides, you can actually explain the generation of control signals that is driven by the internal organization of a processor, mainly in case of a single bus architecture. Also, you will be able to design the complete steps required for a fetch phase of the instruction. Then we are saying again take the same bus of this architecture and take the instruction load R1 and R2, load R2 to R1, that is whatever value is available in R2 you will be going it to R1. So, generate all the control signals and all these steps for this. In fact, just we have seen one instruction for add R1 and R2, you have to repeat it for load instruction load. Again if you are obviously able to design this, then you can easily explain the generation of control signals for any kind of bus. Here we are asking for single bus, you can try it for 2 bus or 3 bus architecture, slightly complicated, but you will be able to do this because more number of buses means less number of steps, which we will again look at we will look in a future unit on this module, we will be looking at 3 bus architecture and then we will be analyzing, but mainly here we are just going for single bus. You can just have a thought that if you are having multiple bus, then together in one bus you can move the value of R1 to R2, one bus you can use for loading the PC to the memory address register and so forth. So, it will be a bit faster basically, but if you are able to design all the steps for this load R1 and R2, then you can explain the single bus organization as well as you can say exact steps required to fetch, decode and execute the instructions. So, with this we come to the end of this unit, and next unit will be going into more depth of some slightly more complicated instructions like jump and conditional instructions and how generating control signals for them. Thank you.